So hi there. And what we're trying to get to is we're trying to get to multiplying polynomials together. But we'll see that everything about multiplying polynomials revolves around what are called the exponent laws for multiplying. Okay, and so what we're trying to get at here, the exponent law 1, okay, deals with the situation where you have, say we'll have something like x to the third, and we want to be multiplying it times x squared, like that. Okay, and so there's a basic way how to handle this, and I'm going to show you where it comes from. We won't necessarily have to do this after we see this, but that's one thing about the exponent laws. They're not things that necessarily need to be memorized. If you ever forget the way they work, you can always write out a simple example like this and do it the long way, and they'll present themselves. Okay, and so we just got to remember what x to the third means. That's repeated multiplication. So that means x times x times x. Okay, and then I have this times right here that I can rewrite down here. All right, and then I have this x squared. That just means x times itself 2 times x times x. Okay, and so down here on this line now, what do I have? I have x multiplied by itself 5 times. So that would mean that x to the third times x squared is equal to x to the fifth, like that. Now, to see a shortcut here, we look at the numbers that we started out with and what we ended up with. Here I had x to the third, and here I had x squared, and I ended up with x to the fifth. So what is that saying? That what exponent law 1 says is that if I am multiplying two things that have the same base, okay, that's important here. They have to have the same base right here. All right, but possibly different exponents. They could have the same exponent. But anytime I'm multiplying two things with the same base, I can add the exponents together. Okay, so like I say, I'm not advising to go through this every time. I was just showing you how the exponent, where the exponent law comes from. Okay, and so we call that exponent law number 1. It's a very basic fact about how exponents work. Okay, and again, just make sure you realize that base needs to be the same. So if I had something like x squared times y to the third, that does not equal something like xy to the fifth or something like that. That's very incorrect. Okay, so those two bases have to be the same. Make sure you realize that also applies to, whenever we write these kind of general expressions, it applies to any situation. So here I was using it for variables. In algebra, we mostly use that. But, just like it works with numbers too. So I could have something like 2 to the 8th times 2 to the 12th. Okay, and that's equal to 2 to the 8 plus 12, which is 2 to the 20th. Okay, and what ends up happening is in a lot of situations where you have really large exponents, 2 to the 8th is a big number. 2 to the 12th is even a bigger number. Okay, and so a lot of times writing those really big numbers, it's longer. A is longer, and B, it'll get lost that you won't recognize that as a power of 2 or whatever base you're dealing with. And so a lot of times we leave expressions written like this whenever we have those large exponents, just to be able to keep up with the actual exponent, and we aren't as interested on what that actual number is. Okay, and then now we're ready to talk about exponent law number 2. It deals with a slightly different situation. You might think they look the same, but it's whenever I have something raised to an exponent, but then I raise that entire expression to another exponent, okay? Like that. So to see how this one works, we start with this, okay? Just don't worry about what it is and that it looks kind of complicated, but we have this thing in parentheses raised to the third power. So that means whatever this is gets multiplied by itself 3 times. And so we end up having x squared times x squared times x squared. And then we can write out what each one of those x squareds mean. That means x times itself 2 times. Okay, and again, once we see the pattern here, we won't have to go through this every time, unless you forget. And that's the thing. Try not to just memorize exponent laws. If you ever forget the way one works, just, use the exponents of 2 and 3, Okay, and then just write out what that means, and you'll see that the exponent laws will present themselves. Okay, but anyway, back to what we were talking about. So we started with x squared, but it was raised to the third power, so I multiplied it by itself 3 times. But each one of those x squareds means x by itself 2 times. So then how many x's do I have in all being multiplied? I have 6 of them, so this whole thing is x to the 6th. All right, so what are we seeing here? If I have an exponent raised to an exponent, I don't add those exponents. That would be 5. But how do you get what is 2 times 3? It's 6. So that's what exponent law 2 says, that if I have an exponent, if I have a base with an exponent, but I raise that to another exponent, then I can shortcut that process by just multiplying the two exponents together. So yeah, just some quick examples with that so you understand what we're getting at there. So I could have, something like, to realize we could have different variables, so I could have y to the 6th raised to the 8th power. And see, this one we definitely don't want to write out because we're going to have this huge string of y's in that case. So hopefully we realize we have an exponent raised to an exponent. And so I'd multiply those two exponents together like that, and see, that's y to the 48th. If we did that one the long way, we would have ended up having to write out 48 x's, and it'd be easy to miscount and so on. Okay, and just remember too, this does apply to numbers, so I could have 3 to the 9th raised to the 4th, like that. And the key thing is I just have a base raised to an exponent, but then that whole thing is raised to another exponent. And so this is 3 to the 9 times 4, which is 3 to the 36th power. That's a huge number. Okay, and so, I hope you're seeing that. 3 raised to the 36th power, I don't know what it is, but it would be this huge number you'd have to write out. Okay, and so whenever we have large exponents, we usually just keep them written with the exponent. It's a lot more succinct way to write what that number is. Okay, so one more exponent law to talk about. We'll call it exponent law number 3. What it does is, what it deals with is if you're multiplying two things or more, and you raise that to an exponent. Okay, and so again, just to see how it works, let's look at this basically. 3x raised to the 4th would be 3x times itself 4 times. Like that. Okay, the key thing here to recognize is that this is just a bunch of multiplications because there's a times between each one of those 3's and x's, like that. And just remember, it doesn't matter what order you multiply things in. Okay, and so what can I do? I can rearrange things where all those 3's are grouped together. I'm just using the commutative law there. All right, and then I can regroup all those x's where they're together. Okay, and don't worry about what 3 times 3 times 3 times 3 is. Just worry about how could you write that as an exponent. That's 3 to the 4th, and then times, and then I have these 4 x's being multiplied, so that's x to the 4th. So I have 3 to the 4th times x to the 4th. Okay, so if you look at this, what ended up happening going, let me write the answer here right next to it so we can see it a little bit better. Okay, and so what ended up happening here, I was multiplying, but I had an exponent on that product. That exponent essentially just distributed down on each one of those quantities. Okay, and so that's what exponent law 3 says, is that if I'm multiplying, or if I have a product raised to an exponent, then I can distribute those exponents down onto each one. Okay, now now there's an important thing here, is that we are multiplying. What we'll see once we talk about division, there is a property just like this for division too. But one thing to try to realize early is addition and subtraction kind of go together, multiplication and division kind of go together, but very rarely does a property for multiplication and division also apply to addition and subtraction. So what I'm trying to get at, this is a very common mistake for people to make. If you have a sum that's raised to an exponent, they'll try to apply this same principle that you can distribute the exponents down on it. So they'll try to say that this is equal to a to the n plus b to the n. That's very incorrect. Okay, So very, very, very incorrect. We don't want to do that, okay? So this property only applies to multiplication, and we'll see later it applies to division as well, okay? But anyway, just to see some basic examples of this property right here, I could have something like 2y raised to the fifth, and so I simply just distribute that exponent down on each one of those. Okay, now I was saying earlier, if we have a really large exponent, and this is a large number, we'll usually keep it written this way. You might want to try 2 to the fifth on your calculator. As a reminder, on your calculator, the exponent key looks like this. It's called a caret symbol. Okay, so for that 2 to the fifth part, you would type in 2 caret 5 and then hit enter. Hopefully you'll see that you get 32 for that. So typically, if this is a reasonably small number, you know, whenever I teach in class, I tell people 1,000 just to give them some kind of base. And so if that number is smaller than 1,000, we'll go ahead and write it out. But if it's if it's bigger than that, a lot of times we'll keep it written in exponent form. Just kind of in the bigger picture, just kind of depends on what you're doing. And a couple quick notes too, just things I thought. So let's just look at general sets of problems and think about which law we want to apply first of all, but also some things I realize I'm getting kind of sloppy about pointing out. What if I had x times x to the third? Okay, so the key thing to realize here is that I'm multiplying and I have two different things, but they have the same base. And so I would want to add the exponent. So this is a situation where we're dealing with that exponent law 1. Okay, so I need to add the exponent. This is the part that I was saying I'll keep getting sloppy about reminding you about. But here the exponent's really obvious that we're adding 3 like that. But what's the exponent on this first part of the product? Remember, if an exponent's not written, there's really a 1 right there. So I would do x to the 1 plus 3, and that's x to the 4th. Okay, so now let's look at one. Say I have negative 2 times b to the 6th, like that. All right, this is another thing I just need to remind you of. We saw this before, but we haven't talked about it in a long time. So I need to apply that exponent. This is actually law 3 right here, where we have a product raised to an exponent. Okay, and so so I need to distribute that 6 onto each one of these. All right, so be really careful, especially if you use your calculator. We're raising negative 2 to the 6th power. To write that and to get your calculator to compute it correctly, you need that negative 2 in parentheses. All right, and then we could just say b to the 6th for that second part. Like that. Try not to try to use that exponent key on your calculator and see if you can get this. Okay, but I maybe pause because I'm about to keep going. But negative 2 to the 6th is actually 64, like that. But the key thing is if you type this on your calculator without the parentheses, it's going to give you negative 64. So you got to be careful to include those parentheses whenever you have those negative numbers, especially. Okay, so anyway, this would be 64 b to the 6th. All right, let's look at one that's similar, and I'll give you an early hint. We'll have to apply 2 laws to it. Okay, so say I have 4x cubed, and then that's squared. Okay, so the key thing about this one is that I have a product raised to an exponent. So this begins as law 3. And what that means is that I'd want to distribute that exponent onto each one of these. But we got to be careful in that second part. So in the first part, it's obvious we have 4 squared. But what am I squaring in the second part? I'm squaring x to the 3rd. So do you see now? Now I have an exponent raised to an exponent. And so now I got to apply that law 2 to that. This happens more often than you would think. And so 4 squared is 16. And then since I'm using law 2, that means I multiply the exponents. So I get x to the 6th. Okay, now we have enough to go on to start talking about multiplying polynomials. Okay, and it's very layered. Okay, the very first step, and this is where we're going to end this video, today is we're just going to talk about multiplying monomials. Sorry, I didn't write that very clearly. Okay, and so remember, these just have one term. Okay, so they're nothing being added. Then once we learn in the next video, we're going to go through the whole picture. But you can see it ends up being all layered. We'll talk about multiplying two monomials. Then we'll talk about multiplying a monomial by any polynomial. All right, and then we'll be able to extend that idea to multiplying any polynomial by any polynomial. Okay, but everything about how you proceed revolves around how you multiply monomials. Okay, it'll seem pretty basic, but it's important to get it down. Okay, so let's just look at an example here. And so say I have one monomial might be 4x to the third, and say I wanted to multiply that by 5x squared. Okay, like that. And so the key thing is, this was like an earlier example, the key thing is since there's times written or not unwritten between each one of those numbers and variables, that means that I'm just multiplying a bunch of stuff. I have this times that times that times that. Okay, and remember, it doesn't matter what order we multiply things in, so we can regroup so that, I don't know why I wrote the 5, we can regroup so we can take that 4 and instead of multiply it by x to the third, we can multiply it by 5 because that's something we can actually do. And then I can take that x cubed and multiply it by x squared. Okay, and so hopefully we know what 4 times 5 is. It's 20. Okay, what's the deal here? I'm multiplying two things with exponents that have the same base. And so that's that law of 1 right there. And so we get x to the 5th. Okay, and that's the actually answer there. Okay, now if you look back to what we did, you can go through all those steps, or that you can put this middle step in here. But if you recognize you're multiplying two monomials, you can kind of see a pattern. Essentially, what did we do going from here to here? We multiplied, remember the term for these things are the coefficients. So we multiplied the coefficients to get the 20, but what did we do to the exponents? We added the exponents. So there's just kind of a phrase you can put into your brain if you want. But anytime you're multiplying monomials, as long as the variable is the same, all right? As long as the variable is the same, then you can shortcut the process by multiplying the coefficients and then add the exponents. All right, like that. And so let's just look at a couple quick examples. All right, so this first one we do, let's do 10x times 4x, really basic one. Okay, except we got to remember something about the exponents. So if we follow it, so make sure you realize we have a monomial times a monomial. Okay, what makes something a monomial is there's no additions or subtractions if you're having trouble remembering. Okay, so we are multiplying two monomials. So if we can go through the regrouping, I'll do it one time. So we can do it like this, okay? Or we can just think about that general idea that we multiply the coefficients. So we have 4 times 10 is 40, and then we add the exponents. Well, how do you get the exponents? Remember that each one of those exponents is 1. So this is 40x squared. Okay, now and you can see right here we would have got the same thing, so it's up to you how you want to do that. All right, and so there's our first example. And what if we had negative 6z to the 4th times negative 3z to the 8th? Okay, then I would multiply the coefficients. You just got to remember how sign numbers work. So we got negative 6 times negative 3. That's two negatives, so it's positive. And then 6 times 3 is 18. And then I add the exponent, so I have z to the 4 plus 8. That's 12, okay? So that would be the answer to that one. Okay, and as always, don't let fractions or decimals throw you. So say I had 5, 6, y to the 8th times 2/3 y to the 6th. Okay, so this one you might want to write out the step unless you're really good with your fractions. But so we multiply the coefficients, and we add the exponents. Okay, and so we're right there and we're doing fine. And so all we have to do is remember how to multiply fractions. So we just multiply straight across, and so we get 10 over 18. And then we have y, 8 plus 6 is 14. Okay, notice this fraction reduces by 2. So we're going to divide each one of those by 2. And so we get 5/9 y to the 14th. And so that would be the answer. Okay, I'm going to leave this video here. It's important to get those basics down so that you can proceed through whenever things get complicated with general polynomials. All right, I hope that helps, and all the best.